those guided readings again?
You have to keep the one. Just keep the ones you have done.
Well, yeah, but you have to mark them. I would do more.
Okay. How about lesson 85? Mean value theorem, Rolle's theorem, practical application of the mean value theorem. Okay, so let's start reading through this. Okay, so there are some old theorems here to just kind of review. Maximum and minimum value existence theorem. So an existence theorem just says that something exists. If f is continuous on a specific closed interval, closed meaning the endpoints are included, then f attains a maximum value, m, and a minimum value, lowercase m, on the interval. This means if you have a continuous section of graph, from point A to point B, somewhere on that section there is a minimum and a maximum. They exist. We don't know what they are or anything, but they exist. That's what that is. Okay, intermediate value theorem. If f is continuous on the closed interval, and n is a number between f of a and f of b, then there's at least one number c between a and b inclusive, for which f of c equals n. You guys remember what that one kind of looks like? If we if A and B are on here, right? And then right here is f of A, and right here is f of B. It says that there is some value C in the interval A to B that equals N, and N is in that interval. Isn't it something like that? I always have to think of the exact wording. Yeah, where this would be f of C, and it equals that value of N. But C has to be in this interval, then that will fall in that interval. And again, it's based on the requirement the function has to be continuous. Okay, that is a key word on calculus problems. Because if you are trying to apply the intermediate value theorem, it's differentiable on the open interval. So that means continuous, no sharp points. So you can take the derivative. Then there exists at least one number, c, in A and B, such that f prime of c is equal to that. And that's basically talking about your slope, right? If you notice f of b minus f of a, it's like subtracting your y values over your x values. Oh, wait, that's actually new, isn't it?
Yeah, a bit. Looks like.
Okay. Okay.
I said something about it being sour and
Okay, well, she wouldn't like my Monday excuse either, so. Okay, so notice again, it's if f is continuous on the closed interval, differentiable, and they say on the open interval because we don't know what those endpoints are doing. Okay, but differentiable, continuous, no hard points. Okay, then there, notice what it says. Exist. So this is another existence theorem. Okay, there exists at least one number c in the interval that the derivative at that point is equal to f of b minus f of a over b minus a, which again is essentially equal to slope if you think about it. Okay, because slope is doing y minus y over x minus x. Now, the easiest way to probably go through this is to look at example 1 and kind of talk our way through this. Because example 1 states to demonstrate an understanding of the mean value theorem by applying it to the function f of x equals x squared minus 2x minus 8 on the interval -2 to 1. Now, before we can talk about mean value theorem, what has to be true?
Has to be continuous and differentiable.
Okay. Has to be continuous. Let's start there. Is that function continuous? And why do you say yes?
It doesn't look
It doesn't look weird.
weird. There might be some fraction or something that makes
It
it.
just gives me good vibes.
Not exactly a great AP answer, although I understand what you're saying. I really do. It doesn't look weird. I get it. Okay. So, first of all, you can think about the fact, what is x squared minus 2x minus 8? It's a parabola, right? A right-side-up parabola. I don't know exactly what it's doing on that interval, but it's some portion of the parabola. Even if it's just one of the sides, it's a portion of the parabola. And then what you can use in calculus is this is a polynomial. Remember our definitions of polynomial, that basically it's terms added and subtracted. And those terms are, combined with, basically variables and numbers being multiplied. If there had been an x in the denominator, that would fall into the weird category, if you would. Okay, that's not a good calculus explanation, but I mean, if an x is in the denominator, or if there's a square root in here, then that is no longer a polynomial function. And so we can't use that reasoning to say continuous. Because this is a polynomial, that right there is justification to say it's continuous because it's a polynomial. Okay? So, yes, it's continuous. Is it differentiable? Is it differentiable at every point? Can I take the derivative at every point?
Yeah.
Again, it's a parabola, right? A parabola is not going to have any sharp points. So that's what I'll put down here in parentheses, is that there's not going to be any sharp points, hard corners, so many different ways I could say that. Okay, so let's check out the mean value theorem then. In order to talk mean value theorem, first of all, what are my A and B values? Negative 2 and 1? Just for reference sake. So my A and B values are the interval, negative 2 and 1. In order to find f prime of c, we're going to have to know f of negative 2 and f of negative 1. So what is f of negative 2? When you put in negative 2, you get 0. Okay. What is f of 1? Negative 9. Now, let's try. So in order to talk f prime of c, right, which c is the, that's what we're trying to prove that there exists. There exists some c value. We just don't know what it is yet. So using the mean value theorem says f of b minus f of a over b minus a. So f of b minus f of a is going to be doing f of 1 minus f of negative 2 over b minus a, which is 1 minus negative 2. Let's see, what is f of 1 minus f of negative 2? Negative 9 minus 0, which is Negative 9. 1 minus negative 2 is 3. Where'd everyone go? Negative 9 divided by 3. There we go.
I guess I'm different for F and negative two and F1, so I'm trying to figure out what those are.
Okay.
Negative 2 would be negative 8.
When you square negative 2, it becomes positive. So that's going to be 4. Negative 2 times negative, minus 2 times negative 2 is going to be plus 4.
Okay, yeah.
So 4 plus 4 is 8.
And
Minus 8 is 0.
okay.
Okay?
1 over 1 would be 1 minus 2 minus 8.
Yes?
So it's 1 minus 2. I thought 1 was negative. I was wrong. But
Is that the problem?
yeah, that's what I'm trying to do
Okay.
this whole time. I've done like 6 times for each of them. I've done like negative 8, negative 11.
I'm sorry, and I just went rushing on because I didn't think that was the deal breaker there. Okay.
It's always down there. Exactly.
It is. It is always the algebra. We've discussed this. That is so true. And I just went flying on without you. Okay.
Of course, it's always the negative.
The negatives. Yep, there you go. Okay. So Nathan's okay with 0, negative 9 now. He's more convinced. Good.
It's always sensitive.
I'm guessing everyone else just believed my 0, negative 9.
I believe it.
Okay, so then I was doing, well, Nathan was trying to figure that out. I did f of 1 minus f of negative 2, right? So f of b minus f of a over b minus a. So that was f of 1 minus f of negative 2, negative 9 minus 0, 1 minus negative 2. So that was negative 9 divided by 3, which is negative 3 is where I was at with that, right? Now, what is that? That is what f prime of c equals, right? Now, let's look. How do I want to do this? The original equation was f of x, right? So can you tell me f prime of x? Can you find the derivative of that? Do we agree? F prime of x is 2x minus 2. Well, if f prime of x is 2x minus 2, what would be f prime of c? Yep, 2c minus 2. In other words, just take c and put it in place of x, right? 2c minus 2. So notice what just happened. Via mean value theorem, we found that f prime of c equals negative 3. Via our typical derivative rules, we found that f prime of c equals 2c minus 2. Where do you see me going with this? Yeah, can we set these equal to each other? 2c minus 2 equals negative 3. Do some math, preferably some correct math. Negative 3 plus 2 is negative 1. Divide by 2. C is negative 1/2. And so, again, this is an existence theorem, right? That there's a number c. So for some value c, what did we find c to be? Negative 1/2. That value that exists, the derivative of the derivative or slope is some value c equals negative 1/2. I'm going to say the derivative is negative 3. So some of that is using the mean value theorem there. And the idea that there exists a point there that equals the derivative at some point. In this case, we found that the derivative is -3, and the point that that happens at is when c equals -1/2. And, you know, keep in mind, the original graph was a parabola. The slope is not always the same, is it? That slope is ever changing depending on where you're at on the parabola. Okay. Try another one. Example 2. You'll notice I kind of darkened that in if you couldn't read what it says. The value of the function f of x equals 1 over x squared minus 1 equals 0 at x equals -1 and x equals 1. The line connecting the point -1, 0 and 1, 0 is horizontal, so the slope of the line is 0. Determine whether the mean value theorem can be applied to prove the existence of a point between x values of -1 and 1, for which the slope of the tangent line to the graph of the function, or in other words, the value of the derivative, equals 0. Okay. So, let's see. We have a function, right? F of x equals 1 over x squared minus 1. It equals 0 at -1 and 1. And it talks about between there, right? Can be applied to prove the existence between the x values of -1 and 1. So what is our interval here? -1 to 1 is the interval we're talking about. And the mean value theorem can be applied to prove the existence of a point in the interval, which the slope of the tangent line to the graph of the function equals 0. Thoughts to get us started? Okay, what'd you say first?
Plug in -1 and 1.
Okay. So jumping right in, plugging those numbers in to find the values. What else was said at the same time? Someone else said something, but I didn't. Besides the hallway, that is. What are my requirements to be able to use mean value theorem? Okay, so have we checked to make sure it is continuous and differentiable before we get started? Is this graph continuous? And it only matters from -1 to 1. Is it continuous from -1 to 1? On the interval -1 to 1, it does include 0. Does 0 work in this equation? No. X cannot equal 0. If we were to graph this, I believe there would be an asymptote at x equals 0. So, can the mean value theorem be applied to prove the existence of a point between -1 and 1? Yeah, it's a no. Since the graph is not continuous at x equals 0, the mean value theorem cannot be used. Okay, I'm ready for example 3 when you are. Demonstrate an understanding of the mean value theorem by applying it to the function f of x equals, that is x to the 2/3 on the interval -8 to 27. So what should I start with here? Okay. He's not going to make that mistake a second time. So we will start with the question. Is this continuous on the interval -8 to 27? Which I think there'd just be one primary value I would question. And that would be 0. Because you can, remember 2/3 is taking a cube root and squaring it. Can we raise 0 to a power? Yeah. So is it continuous? Yes. And then we need to talk, is it differentiable? Thoughts here?
I think it should be.
I feel like it should.
Part of like a sideways parabola, I feel like.
So what does, if we're going to talk about what the graph looks like, x to the 2/3. Can you visualize what x to the 1/3 looks like?
It's just a sideways cubic.
Okay, so we talk about x to the 1/3 is a sideways cubic, right? Now what does x to the 2/3 do?
It just makes the left-hand side of the y-axis positive.
Okay, so x to the 1/3 looks like this. X to the 2/3 is taking this and squaring it. So if we square it, it takes whatever's negative and becomes positive, right? So this part over here is already positive. And this part over here, what's it have to do? It's going to flip up and also become positive.
Then you have a hard point at the origin.
And this is where it's, you know, the more we know about graphs, the more it's helpful, but we do. That is a hard point, sharp point. And the key would be if you take the derivative and try and plug 0 in. 2/3 x, or x to the 2/3, 2/3 x to the -1/3. X to -1/3 is going to put x where? In the denominator. And can you put